Good day, ladies and gentlemen. Today we're going to go back in time and review one-to-one and inverse functions, which we need to have a good, solid understanding of to be able to talk about these inverse trig functions. And I'll tell you, these inverse trig functions are an interesting topic, and they can be a little bit confusing. So to try to prevent a lot of that confusion, we're going to go back and have a review on one-to-one functions. So let's go. So one-to-one function, a one-to-one function, a function is one-to-one if and only if for any value in the range, say b, there's one and only one value in the domain, say a, that maps to b. What that means is if f of a is equal to f of c, then a is equal to c. So these guys are range values. These guys are domain values. Don't get freaked out by that definition. Here's how you're going to check to see if a function is one-to-one. A function is one-to-one. Two things. A horizontal line will intersect the graph of f of x at one and only one point. If that happens, the function is one-to-one. If f is a continuous function and is always increasing or always decreasing, then f of x is a one-to-one function. We're going to need to we're going to need to remember these two properties of a one-to-one function. What we're talking about then, if a function is one-to-one, then it has an inverse. And we're going to be talking about inverse trig functions. So let's go through some examples about some one-to-one functions. Here I have example number 1, f of x is equal to 3 plus 2/5 times x minus 1. This is a linear function given in point slope form. This linear function is always increasing. It's always increasing because of this slope right here, 2/5. It's always increasing. The slope is up 2/5. So yes, this is a one-to-one function. And if I want to find out what input goes to 7, there's only going to be one input that goes to 7. And what I'm finding here is if this output over here is 7, what maps to 7? And I've solved this, and I'm going to try to make this as quick video so I get through everything today. So I've done the math here. I put a in for my function right here, a minus 4, and then I've simply done some simple algebra, and a is equal to 14. So this 14 comma 7, this is on the graph right here. This is 14 comma 7. And there's only one input that maps to 7. Okay? Note, all non-constant linear functions are one-to-one. All non-constant linear functions are one-to-one. That's good to know. Let's go back here to example number 2. Example number 2 here, we have this quadratic function right here. Okay, this quadratic, negative 3 plus 2 times quantity x minus 1 squared. Well, this guy has the vertex of 1 comma negative 3. This is the vertex. And we note that f of 0 is negative 1. This guy right here is 0, negative 1. And this guy right here is 2, negative 1. And right away we see two different inputs that map to negative 1. So this thing can't be a one-to-one function by definition, because 0 maps to negative 1 and 2 maps to negative 1. The other way that we can determine right away that it's not a one-to-one function, because this thing decreases, then increases. And if we look here, we just take let me take a vertical line here, do a yellow vertical line. I'm hitting something here. Here we go. Now I think I have it yellow. If I take this yellow vertical line, let me get this other rascal out of there right now. Let me get him, just move him out of the way. But if I take this yellow vertical line, you see, or horizontal line, excuse me, look, it's crossing that graph more than once. That's another reason why I can say this function is not one-to-one. In fact, no quadratic functions are one-to-one, because the horizontal line test will never work on a quadratic function. Oh, interesting to note, about trigonometric functions. We're going to use this to talk about inverse trig functions. So just remember this discussion. It's a good discussion. So let's go to another example. And keep in mind, you can always pause the video if I'm going too fast. So let's go to another example. 3 right here. The infamous rational function. You should be able to graph this guy really quick right now, and I'm going to graph it really quick. I'm going to look at this vertical asymptote right here. This vertical asymptote, I better get a better color here, get this funky orange color. This guy has a vertical asymptote at -3. Well, I'm sorry. I'm going to try to match this up with what's in your notes. And what's in your notes, this guy is going to be an x -3, and this guy is going to be an x +1, because I want the notes to match up with what I'm doing. If that's the case, then this guy is going to have a vertical asymptote at 3, because that's what makes the bottom 0 and the top not. So this guy here is x is equal to 3, vertical asymptote. This guy has a horizontal asymptote, but if I put Kerbillion or negative Kerbillion in, it has a horizontal asymptote at 1. So this value here is y is equal to 1. Y is equal to 1. And I notice that this thing crosses the x-axis at -1, because that's where the top is 0 and the bottom is not. So I'm going to put this rascal in right here, put this point -1. If I put 0 in, it's going to be -1/3, and this graph is going to look like this real quick. Whoop, easy. Whoop, is easy. And it doesn't squiggly like this. And now, my question is this function 1-to-1? Is f of x 1-to-1? And right away, hey, yeah, because this graph is always decreasing. So f is always decreasing. So yes, f of x is 1-to-1. Okay, let's continue on with the video. Now we're going back to the definition of a 1-to-1 function. We've already given you that. F of x is a 1-to-1 function if and only if any value in that range of f, say b, there's one and only one value in the domain of f, say that maps to b, and that means f of a. If f of a is equal to f of c, then a is equal to c. This definition right here, this is a typo. This is a typo in my notes. So what we're going to do is we're going to take this, we're going to cross that baby out, because that's wrong, dog. This is the definition of 1-to-1. This guy here, right here, that was the definition of a function. So, and I'm going to do a little mapping. I'm not quite sure if you did any mappings last semester, but I'm going to do a little mapping right here. I'm going to do a little mapping right here. And I think I got it down. Yeah, well, I want a solid line right there. I think I got a solid line. Here we go. So here's an example of a mapping function. So I'm going to go 2 maps to 5, 3 maps to 8, 5 maps to 11, 8 maps to 15. And so this is what we call a mapping function. These are the domain values right here. These are the domain, and these are the range. I have this mapping. So f of 2 maps to 5. What does that mean? Well, the point here, 2, 5. I can talk about that point, and I can talk about this point 3, 8. I can talk about this point 5, 11, and I can talk about this point 8, 15. Those are points on f. So does this function, is this a 1-to-1 function? Yes, indeed, it's a 1-to-1 function, because every domain has one and only one range that maps to it. And this is a very, very important property of one-to-one functions, the domain of the inverse or one inverse function. So if a function is one-to-one, boy, I almost wrote over that. So if you look at this line right here, if a function is a one-to-one, then that function has an inverse. And that's where we're going, is when a function has an inverse function. When does it have an inverse function? A function, if it's one-to-one. And here's the two main properties of an inverse function. The domain of the inverse is the range of the original. The range of the inverse is the domain of the original. Let me move this rascal right over here. So this guy is one-to-one. So I'm going to do a mapping of the inverse. And it's very simple. 5 then is going to map to 2. 8 is going to map to 3. 11 is going to map to 5. And 15 is going to map to 8. And this is the domain of the inverse. This is the domain of the inverse, and we're going to denote the inverse f of -1. And I have that in your notes. It didn't come up when I copied it into my Smart Notebook file. And this right here is the range of the inverse. And you notice that this domain was indeed the range of the original function. This guy right here is the same as this guy. The domain of the inverse is the range of the original. And the range of the inverse is the domain of the original. And now I can simply note the points on the inverse. The points on the inverse are 5, 2. Oh, it's just these guys flipped. 8, 3. 11, 5. And 15, 8. Keep in mind, we're not doing anything. We're not doing anything that's not going to be super important when we start talking about these inverse trig functions. I'm just trying to clean this up a little bit. I wonder if I can just erase those rascals. I think I can. Okay. So let's go to the next page. And it's easy to find the inverse of a map. You can just flip the points. Okay. So here we go. And again, I can't speak more importantly about how these properties are important. It's a funny statement for inverse functions. The domain of the original becomes the range of the inverse. The range of the original becomes the domain of the inverse. Very simply put, if AB is on the graph of F, then BA is on the graph of F inverse. And here I have another linear function right here. I have a linear function, an increasing linear function again. And I know it does have an inverse because this guy 1/5, so it's an increasing function, strictly increasing. And so it has an inverse. And if I put -4 in, -4 minus 1 is -5, times 1/5 is -1. 3 minus -1. This guy right here, this is going to be f of -4 is going to be +2. -4 times -5 times 1/5 is -1. 3 minus -1 is 2. If I put 1 in, 1 minus 1 is 0. 1/5 times 0 is 0. 3 plus 0 is 0. And if I put 6 in, it's going to be 4. And here are the points on F. -4, 2. 1, 3. And 6, 4. This guy does, F inverse does exist. So points on the inverse, F inverse. F inverse, let me write that correctly. The F inverse guy right here. Points on this guy are simply going to be 2, comma, negative 4, 3, comma, 1, and 4, comma, 6. Okay? Next page. Here's the formal analytical definition of inverse functions. And it has this composition of it. If f composed with its inverse, f of f inverse, if that equals x, and f inverse of x equals x, then f and f inverse are inverses of each other. This is important. This is going to be difficult when we start talking about inverse trig functions. And keep in mind, that's where we're going. And I remember reviewing this property with you, this definition with you, last semester when we were doing formal inverse functions. So this is a review, a very important review. So here's example number 3. If I have this linear function right here, 2 plus 1/3 x minus 5, and this guy right here, 5 plus 3 x minus 2. First thing I'm going to do is I'm going to take these two linear functions. I'm going to write them in slope-intercept form. Distribute to 1/3. 1/3 times 5 is negative 5/3. 2 minus 5/3 is 1/3, so that's f of x written in slope-intercept form. Distribute the 3 here. 3x minus 6 is going to be 3x minus 1. That's g of x. And now I want to know if these guys are indeed inverses of each other. So the first thing I'm going to do is find f composed with g of x, f of g of x. So wherever I see x and f, I'm going to put g. So I'm going to take this rascal right here, and I'll put him in that x. Distribute to 1/3, x. 1/3 times 3x is x. 1/3 times negative 1 is negative 1/3. Plus 1/3 is x. Bam. Check OK. And now I'm going to take g of f of x. I'm going to put this guy right here. I'm going to put him in here. And 3 times 1/3 x is x. 3 times 1/3 is 1. 1 minus 1 is 0. And so check OK here as well. So this is a brief little video, a review video, so that we can talk about inverse trig functions. So I'm going to go back and review what we've done. You have an assignment. You're going to do this assignment, but here's what you're going to be looking for. You're going to be looking for, does the graph always increase or always decrease? If it does, if so, f inverse exists. If so, f inverse exists. And then you're going to be looking for this. If you do have a function with an inverse, if AB is on f of x, then BA is on the inverse. I.e., the domain right here, the domain becomes the range, and the range becomes the domain. Good luck. Have fun. See you soon.